Welcome to Chemistry with Caroline. In this video, we're going to look at the synthesis of ethers via the Williamson Ether Synthesis. So this synthesis involves the combination of an alkoxide ion and an alkyl halide. It will only work for unhindered alkyl halides, and we'll talk about that in a minute. Here I have the alkoxide ion on the left. That is going to act as a nucleophile in the Williamson Ether Synthesis, but it can also compete as a base, and so that's why the hindrance of our substrate comes into play, the substrate being the alkyl halide. When you have a primary alkyl halide, like the one we have here on the right, you're going to get an SN2 style nucleophilic attack. So this alkoxide ion oxygen is going to attack the electrophilic carbon that the bromine is on, and the bromine leaving group is going to leave at the same time. So that's an SN2 type reaction. The nucleophile attacks as the leaving group leaves, and that will give me this compound right here. So I'll draw a squiggle through the bond that we made. This carbon right here is the one that had the bromine leaving group on it, and this right here is the alkoxide ion that attacked. So this reaction will work for unhindered systems. So when you have a methyl or a primary alkyl halide, you will see substitution reactions, and you'll be able to synthesize an ether. Let's go to the next slide and we'll look at what happens as my substrate, the alkyl halide, becomes more hindered. So in this example, we have a secondary alkyl halide and we still have our alkoxide ion. And so we intend this to be the nucleophile, but it's also a really strong base. You have a negative charge on an oxygen. And as our substrate, our alkyl halide, gets more hindered, you're more likely to see an elimination reaction. A base can come to the periphery of the molecule and pluck a proton off, as opposed to going all the way in and acting as a nucleophile. So what's going to happen instead of the desired Williamson ether synthesis is an elimination reaction via an E2 mechanism. And so this bromine is still going to be the leaving group, but now instead we're going to have elimination type products. So remember, the next door neighbor positions to the alpha position where my leaving group are the beta, and in this case the beta prime positions, because they're not identical to one another. And so I'm going to draw my hydrogen on my beta prime position and then show you what would happen instead. So the lower energy pathway is elimination when the substrate's more hindered. So the alkoxide ion is going to act as a base as opposed to a nucleophile. It'll plug off the proton from a beta position. Those electrons will fold down and the leaving group will get kicked off at the same time. So this is an elimination reaction. So you're going to proceed through an E2 mechanism, and it would give you an alkene there. So this would be one of your beta prime alkenes, and then I'm just going to put it all the way over here, but you end up making an alcohol, right? This is the conjugate acid of your base starting material that you worked with. So then you would get all of the possible alkene products. And so if you can get the E, you could also get the Z stereoisomer of the beta prime. And then also you could have elimination of the proton that's terminal, giving you the beta product. So you end with a mixture of alkenes as opposed to the ether that was desired in this synthesis. So you need an unhindered alkyl halide starting material in order to proceed through an SN2 mechanism and secure that desired ether product. So this has been a look at the Williamson Ether Synthesis. If you found this video helpful, please like, subscribe, and share with your friends. Thanks.